So, dark matter, part two. I like talking about dark matter because it's such a mysterious, it's one of the open mysteries in science at the moment. Here is, we've learned about our Milky Way, we've learned all the things that we could learn from light, and this is how we learn about most of our universe, and we're very clever, and so we've gotten indirect evidence for various things, but then we look at what the constituents of the Milky Way are. The majority of stuff in the Milky Way is something that we have no clue what it is. I find that exciting. Like, I'm taking you on a scientific journey and you get to a point where you go, we have no idea what this is. So today I would get you through all the pieces of evidence that we have from galaxies that yes, they contain more stuff, they contain matter, more matter than we are aware of. Than we can account for with light. So dark matter being the big mystery, and next week we'll do galaxies as a sort of what we learn from them. And so I'm just taking the Milky Way, and I'm sort of going a little bit further and saying where we got our evidence for dark matter. Again, we're here. Here's the center of the Milky Way. This is my crummy JPEG, and so I'll be replacing that with the Gaia ones. But the neat thing is that we know all the constituents. And we had a whole discussion, and we'll talk about this next week, where it took us a while to figure out that we were here and not here, or what the shape of the whole Milky Way was, but also whether or not this was it. Because this is where all the stars sit. We can see a bulge, okay, fine, so maybe that's it. And then there's these little smudges called the clusters. And oh yeah, then there's this third thing, which we call nebulae, and they seem to be everywhere, but it's hard to tell if that's something like our Milky Way or if they're outside of it. And so once we actually tallied everything up, and so here you can see, for example, interstellar matter with all its gas and dust and metals, meaning anything not helium and hydrogen, all the stars, whatever is left after you have a star, supermassive black hole, the planets. If you add everything up, we basically need that again or so to get the dark to explain how the whole thing is rotating, how the whole thing moves, right? So that got us everything. So what is dark matter? Is it space gerbils, gas, dust, and other stuff that isn't light emitting, very dim stars, planets and black holes, something that has mass but does not show itself by emitting any wavelength? All right, get your voting cards out. This is what I always do. Voting in 1, voting in 2, and voting in 3. I see everybody holding up the whole center screen. Thank you. Yes, it's something that has one characteristic and one characteristic only. So if we think of normal stuff, we're a little biased here, right? We think of ourselves as made out of normal stuff. This is normal stuff. Why? Because I encounter stuff like that all the time. So that must be normal. And that reflects light, it emits light, it does electromagnetism is the physical term for that. It also does gravity, and it does two other forces in nature called the strong and the weak force, but we don't have to go into that. Essentially, normal stuff behaves in a way that our physics laws or our rules in physics seem to be working. Except this just does one. It just does gravity, and so we can figure that out by saying, like, okay, well, if I see something moving and I know at what radius it is, how far out it is, I can, if I get the velocity and the radius, I can measure the mass, right? I can move this r over here, I can divide the whole thing by g, and then I have the total enclosed mass. So if I can measure how far out something is and how fast it's orbiting, and just say, like, well, it's probably a circular orbit, we're close enough. If something is orbiting my galaxy, I can tell how much mass is enclosed to keep that mass in there. So if I do that, I have to measure this, and then I can get the total mass enclosed. So if I do that, and I go like, yeah, the further out I go, I can sort of tally up. Here's a lot of light here, so it kind of goes like it goes up immediately, so I can go very, very fast, and then I just add a little bit extra. So this is sort of the maximum speed I'm allowed to go without leaving orbit. But if I then do that and actually see how fast the gas is moving, it moves much faster. This stuff should be leaving orbit, but there's so much mass that it keeps it going in a circle. Okay, so that was what was discovered by Vera Rubin and the people at the Westerbork Radio Telescope, which is pretty close to my hometown. And so the difference is, A, this is what you expect sort of to happen. Not quite the motions of the planets around our sun, but something pretty close to it, so it should be dropping off speed-wise, right? Remember that the stuff in the far outer solar system takes forever to orbit because it actually goes slower and slower. So we expect something like this. We're seeing this. We're seeing case B. We're seeing stuff move in the outskirts way faster than it should be. That means that there is stuff here and quite a lot of it. And so it can be just all stars. There has to be that extra bit. All right, what was the constituents of the Milky Way again? Interstellar matter, or do we start with dark matter and planets, dark matter and stars, dark matter or interstellar matter? Voting in 1, voting in 2, voting in 3. Everybody was here Tuesday and remembered. Yay! All right, fantastic. So we have this dark matter, and we have no idea what it is. We discounted a whole bunch of stuff already, and so this is how you can do science. This is what I was trying to say on Tuesday. You can go with, I have a hypothesis, I'm going to test it. Great. If you then get, this wasn't it, you're still contributing. This is a human bias in science. You want to discover something. That is the thing that you want to tell everybody about. That will win you Thanksgiving. It'll be great. You go like, I discovered X. That's the thing that you want to do. But you're helping science if you go, it wasn't this, which means that nobody has to spend time on that anymore. It's not as exciting. There's no eureka moment, but you do discount that this doesn't work. This also goes for most other sciences. A non-result helps science as a field. It doesn't help you as personally as a scientist to get on the front page of the New York Times or what have you. But as a field, it works really well. So we've discounted a whole bunch of different canons that we could come up with. And for galaxy rotation, so that was 1980 by both Vera Rubin and the radio astronomers in the Netherlands. And of course, I'm mentioning that because I literally got my PhD at the same institute, right? So this is, so it is on the one hand, you had a bunch of Europeans finding this rotation, and on the other hand, you had Vera Rubin and her supervisor here in California finding with a completely different telescope. Sadly, she passed away. So I met her, and every astronomer who's ever met her always has sort of the same story. Wow, she was so cool and encouraging. This was one of those people that you go like, I hope she gets a Nobel Prize just by sheer personality alone, but also because she was one of 2 groups that found this. And you have to be alive to get the Nobel Prize, which I think is personally an issue. The other part is that, yes, we had on one hand, we had Vera Rubin, and on the other hand, it wasn't really one person, it was a group of people, so it was sort of hard to pick who you would pick for that. But yeah, she should have gotten the Nobel Prize. This is sort of a consensus amongst astronomers that she should have gotten that. For example, so she measured it with glowing gas, and that's the red line, and the blue line is what they did in the Netherlands with that's the colder gas, that's the radio observations. So with radio observations and optical observations, 2 different kinds of telescopes, 2 different kinds of techniques, 2 different groups, and 2 different continents find for the same galaxy this rotation curve. It stays flat, it doesn't go down, it stays flat, and the further you go out, and then even other people later actually go and check that. Yes, there are discrepancies, yes, we don't completely agree, but they all seem to agree that it stays flat. And why do I show you this one? This is my plot. It's because, hey, in 1980, and I get to do this, in 1980 she wrote 2 papers, and so the 1980 paper is like, hey, I think this is dark matter in these galaxies. The other one says, I think this galaxy is really big. It's really oddly big, because this is the Milky Way, and this is this galaxy, put on the same scale. So I think it's actually rather large, and I noticed that all these other galaxies that she had as examples had Hubble pictures of them, and this one didn't. And it was like, well, why don't we make one and then sort of call it Rubin's galaxy? And so this is my calling card galaxy, or basically this is Vera Rubin's galaxy. I've been calling this Rubin's galaxy distances, and it's a nice, pretty picture of a huge spiral galaxy, 10 times the mass of our Milky Way, about 5 times the diameter. It's enormous, but still dark matter, completely held together by a huge halo of stuff that we don't know. So galaxy rotation is, however, not the only evidence. If there's a large mass of stuff in a galaxy that isn't glowing, and Einstein is right with the whole E is mc squared thing, then light, which also has energy, must also encounter that the effects of gravity, effectively the curvature around the mass. And enough mass in one place can act as a lens. And so this is the last part. This is the other galaxy mass part that I think is convincing. If you look at a large mass of galaxies and stuff, and you put a lot of mass in here, then if you have a more distant galaxy, the light lenses around it. Or you have a cluster of galaxies, and then the light from the distant galaxy actually takes several paths around to end up with the same picture of the distant galaxy, but on different spots. That only happens if you have enough mass here in the center. So you can sort of see these arcs here, here's one streak. Those happen when you have a gravitational lens. It is literally being lensed. I'm just going to assume that you've looked through the bottom of a Coke bottle or like a glass with a thick bottom, for example. It sort of acts. It's not like your glasses. It's sort of like a broken lens. But you can see the weird distorted light from the distant galaxy, and often you get more than one image of the same thing. If you do that with like through a Coke bottle, you look through it as if it's binoculars. Your uncle sort of becomes two different blobs that are looking kind of odd. Well, that's what's happening here. You get an arc on this side, and you get an arc on that side. Now the question is, hey, how did you guys know that that's the same galaxy? Well, spectroscopy again, right? We get the fingerprint. We get, not only do these two things have the same color, so there's a big elliptical galaxy here, and then there's an arc here, and an arc here, and we check what the light is, and it has exactly the same distance and redshift and spectrum, which means that's the same object. And so, very, very recently, if you all have better eyesight than I do, so check it out. This is an elliptical galaxy observed by the Euclid Space Telescope. And so this is this very big mass. But as you look closer into the center, does anyone see that little circle there? Yes, no, I'm looking at it. Yes. Okay, great, fantastic. So if I blow that up, I'm seeing almost a perfect arc around the center. So somewhere much further away is a small galaxy that's basically now being lensed, so it's arced around, and this is called an Einstein ring, because this is an effect of Einstein's general relativity, the way that we understand gravity now. And so there is a bunch of mass, and yes, a lot of it is stars, and the rest is dark matter. I mean, there aren't enough stars to do this. The lens, the arc would be smaller if there, smaller. Yes, the arc would be smaller if it were, if it didn't have extra dark matter as well. So we can measure it in all kinds of ways. In fact, we're finding these lenses everywhere. So this is the Euclid Hall. So you can see these little arcs around all kinds of galaxies, and this is a kind of fun thing that you can do as part of an astronomy project. So people look for these things with something like the Galaxy Zoo, and finding these things is also machine learning. So AI, I hate the word AI, I'll be honest. It is machine learning, right? It's not intelligent at all, but it is very good at finding a little dot with a ring around it. And so it's finding these things all over the place. So we see this evidence everywhere. And you get these also around groups of galaxies, you get these strange arcs, these strange streaks, and that is a more distant galaxy completely bent out of shape. And that only works if you have a bunch of mass here that you can't explain with just the stars. This is a James Webb picture with the same idea. This is a group that I'm working with. You can see these distorted galaxies and these little streaks everywhere. So how do we know it's the same galaxy? It's an assumption, but it's only a logical solution. We took a spectrum, nothing in nature is shaped like that. All right, voting in 1, voting in 2, and voting in 3. I got majority B. Yes, we took a spectrum. So usually I have to follow up and check later. I have a little group work. I'm doing that in a minute because I also have and Drew just warned me, a rather longish show with about dark matter, how we're trying to find it. This is my favorite one of all of them. There's 2 galaxies as a little group, and there is a big smiley underneath. Right, so if you see the cosmic smileys, these cosmic smileys are extra evidence for dark matter. It's never a perfect lens, so this is what you expect if you look through like a lens in if you have like a DSLR, for example, you take the lens off, that's what you look at, oh, that looks crisp. You know, what you should be thinking of is like is something like a bottom of a glass or not quite perfect, right? It is not a perfect smooth thing, it is a lumpy bunch of galaxies, but looking for these little arclets is now big industry in astronomy to find the evidence for how much mass there is everywhere, how much dark matter there is everywhere. And the last part that I find really cool, so I'm just going to sneak that one in here, is not only do you get that lens, but it takes a different amount of time to take every path, right? So because I'm starting here, not quite in the middle, starting one step over here. If I want to run to Drew this way, it takes me a little bit longer than that way. So I'm being lensed by everything here in the middle. All of you are pulling me to the center, and I'm going to run that way or run that way as a bit of light. If I do that, and I split myself up into 2, right? I go, twin me is going this way and that way. That way it's going to take a little bit longer. It's going to get to Drew a little bit later. So if something explodes in this background galaxy, like a supernova goes off, we see the supernova go off first in the shortest time, like this one goes off first, then that one, and then that one. We've actually seen this happen. I find that absolutely amazing. We see the same explosion 4 times at different times because the light took a detour. And it only took that detour because the space is curved because of all the stuff in between. It wouldn't do that, otherwise we would see 1 point. And so we know this works, and that timing actually tells us exactly what that lens looks like. So yeah, there's extra stuff there. There's something else that does one thing. It doesn't do anything else to light. It doesn't absorb it. It doesn't emit it. It doesn't obstruct it. But it does bend the space around it so the light has to go on a curve. And that means there's only one thing that's bends space, and you need mass for that. So it has one characteristic. It's stuff. It has mass, and we don't know anything else about it. So yes. Dark matter is a new ingredient for galaxies. Evidence is completely gravity-based. Rotation of galaxies, distortion of light, those are sort of 2 ones on the galaxy scales. There is one more. We'll talk about that when we are in the last week of class, because I'll talk about the universe as a whole. The bigger galaxy, a group of galaxies, the more dark matter they have. The problem doesn't get any easier if you make the galaxy bigger. Actually, there seems to be more mass in there. So, let's see, where is it? I have this little group work where you can sort of estimate where that. And then we'll swap over to what we're trying to do about it, right? Because having an unsolved mystery is just luring everybody in. Its problem is it's an unsolved mystery since 1980. So yeah, there's like 3 people who were here in 1980, I think. So it is a lifelong mystery for some. We're not done with it yet, but I'm optimistic that we can solve it, right? Right now we've solved every great physics mystery eventually. You just have to do that. is not gonna